Hi, this is the third installment to the Magnetism and Matter series, where in the previous video we had this is the third one. In the previous video we had discussed about the magnetic dipole moment which is acting from the south towards the north inside the magnet, and we had obtained the expression for magnetic field intensity due to a magnetic dipole having a dipole moment m vector uh, at the axial and the equatorial lines, along the axial and the equatorial lines. We will be discussing a few more terms and about the magnetic materials that are present. So to start off, we have some terms which are associated with magnetism, one of them being magnetization. Now when a magnetic material, be it any magnetic material, it will have a net dipole moment. See, a magnetic material, let's consider it in the bar form, and it has its dipoles to be aligned like this, the arrowhead giving the north polarity while the tail, the other end, giving the south polarity. So in this case there will be a certain net magnetic dipole moment over this given volume of that, let the volume be V, so that over that given volume it will have a net magnetic dipole moment where it will have a net north pole on one side and net south pole on the other side. So we define the magnetization. It is usually denoted as capital M. So in some other books you may see this to be you may this term may be in the form of intensity of magnetization, also known as intensity of magnetization. It may be using the notation as I instead of capital M. Uh, that's as per the text that has been given in that book, but here we are using capital M as the magnetization, which is also the intensity of magnetization. Intensity in the sense that how intense is the magnetic dipole moment in that region. So definitely this is just the magnetic dipole moment. The density of the magnetic dipole moment will give me the magnetization. So that means we will be having a net dipole moment associated with the magnet per unit volume of that magnet. So this is how we define the magnetization or the intensity of magnetization of a given magnet, or even a given magnetic material. Now remember, a magnetic material which can get magnetized, it can acquire a certain dipole moment over a given period of time, and as a result of that you have the net dipole moment, and the net dipole moment distributed over its entire volume gives the magnetization. Now as far as the units are concerned, the unit over here, as you know, in case of dipole moment you have the unit as ampere meter squared, and in case of volume it is meter cubed. So this is ampere meter inverse. This is the unit of the given magnetization that we just obtained, and the dimension obviously is L to the power -1, and A, M being 0 and T being 0, no mass and time involved. Now we had already discussed about the magnetic intensity, that is the H vector. So we define another term that is known as susceptibility. This is magnetic susceptibility, usually represented by this symbol chi. So the magnetic susceptibility is just giving us the idea how susceptible is a material to get magnetized in the presence of some external field. Now if it is subjected to some external field, definitely it will start getting magnetized, and because of that it will acquire some net dipole moment. So how much susceptible is a given magnetic material to get magnetized. And how do we know that? We just know that by the magnetization value that it acquires. Magnetic dipole moment per unit volume, that is the magnetization that we just studied. The magnetization that is acquired by the given magnetic material over the magnetizing force that is provided to it. So this is the magnetization per unit magnetizing force that is provided by the external field. That is how we define the susceptibility of a given medium, sorry, of a given magnetic material. Now, because as you can see, this as we had discussed, has this same unit, and this has the same unit as well. So this obviously is just an index, it's just a number, and it will have a certain value. That value obviously depends on the how much the magnetic dipole moment that it acquires over a given over an applied external field. Now, with this uh, these parameters discussed, we can just relate now. Now, we know that there's a certain thing called relative permeability, is analogous to relative permittivity in case of electrostatics. The relative permeability is simply the ratio of the permeability of a given medium with respect to the permeability in free space. So this is for a given medium, and this is obviously for air or vacuum or free space, be that as it may. We can relate these two, and how do they relate? So here is a magnet, piece of magnet, and or a magnetic material, so as to say, and it is subjected to some external magnetic field. The external magnetic field obviously is acting in free space. As a result of that, this magnetic material starts acquiring a certain dipole moment. Uh, the the orientation of these um, dipoles within the given material probably would have been like this, the above case. They slowly start to orient themselves as per the external field, and they achieve this kind of a net dipole moment. These magnetic materials obviously can acquire a considerable dipole moment when subjected to an external field. Depends on the type of magnetic material that we are using. There are different types of magnetic materials or magnetic substances that we'll be discussing later on. So in this case, if they acquire a net dipole moment, there is a net magnetic field associated with that material, so let that be Bm. Now, with the external field and the field that is acquired by this, which again comes out externally and completes the loop, because they are in the form of closed loops. So there is a net magnetic field that is associated, which is actually the vector sum of the external field that is being applied and the magnetic field acquired by that material. So with this relation available to us, what we have is, now if you remember in the previous video, you can just move over to the previous video and you will see that the magnetic field for a mixed kind of a medium, where for in case of air or vacuum, the magnetic field is related to the, or the magnetic intensity, magnetic induction vector, that is B vector, is related to the magnetic intensity or the magnetizing force by this relation mu naught times of H. B naught is equal to mu naught times of H. And for any other sort of a material or for any given medium, here that being the net magnetic field will be simply some mu, because there is a material involved over there, so mu times of H, right? And on the other hand, you have the value for the material Bm to be simply uh, mu naught times of m here being the magnetization. Now how is this relation available to us? Now let's check that. Now, we already know, actually we that's a separate segment, but let me share it with you. We can relate the a given magnet to a solenoid. Suppose we have a bar magnet that can be related to a solenoid which is carrying current, just like the one I have drawn right now. And there will be a net south pole and a net north pole. It will have a certain polarity because a coil carrying current behaves as a dipole, magnetic dipole. So, and the magnetic field that is associated with this kind of a solenoidal arrangement, so the magnetic field in this case is simply mu naught. Of course, it is an air core solenoid, so there is no other medium other than air between it. So it is mu naught times of n times of I being the amount of current that is flowing, and mu naught ni is simply n here is the number of turns per unit length, and I is simply the current that is flowing across the loop. Now in this case, in case of a material which is being compared to this solenoid, there if we use this formula that we have over here, that is mu naught times of m, then it is mu naught times of, instead of m, what we can write is it is dipole moment that is acquired per unit volume. The volume is obviously some cube of some length maybe, but it has obviously the dimension of L cube, the volume. Now in that case mu naught. Now the dipole moment of the dipole which is in this solenoidal arrangement, as I said, the solenoid behaves as a magnetic dipole. The dipole moment in this case is not the general formula that we just studied in the previous video. The dipole moment in this case is I times of A, where A is the area of cross section of the loop, of the face of the loop. So the face of the loop, like this face is having an area A, which is completely the same for the rest of the coils as well. So this is simply I, that is current, multiplied with area. If I put that value over here, so I have an I, that is the current, multiplied with some area. Obviously we do not have a single loop, we have n number of loops, if you remember. So n number of loops will have n times the current flowing, because each current carrying element will be providing some magnetic field, will be contributing to the magnetic field. So this is n times of I multiplied with a as it was there, I into a. So this is n times of I into a, right? And that divided by volume. Volume, as you know, is simply L cube, and A is the square of length. So mu naught n I L squared divided by L cubed. So dimensionally you have the length to cancel out one another. One length remains in the denominator, that gives me the number of turns per unit length. So this is mu naught times of n times of I, which is the magnetic induction vector in this case. So this formula that we have for a magnetic induction vector, that is exactly the case that we obtained over here, stands correct for the given magnetic material. So on the right hand side, for the magnetic material that we are using, supposedly it is compared to an air core solenoid, it will have its induction vector to have the value mu naught times of the dipole moment, mu naught times the magnetization. And on the left hand side we simply have a mu times of h as suggested over here. Now as we can see, the h can be taken common. If we take h common on the left hand side, what we have is inside the bracket we have mu naught. In fact, mu naught can be taken common as well, so mu naught can get lost from that place. We have simply 1 plus m divided by h, and what was that? That was equal to the susceptibility that we just obtained on this place over here. So this is mu, and that mu naught can come down over here. The h can get cancelled on both sides, and we are left with 1 plus chi, that is the susceptibility. What is mu plus mu divided by mu naught? This is simply mu r. So all we have a relation between relative permeability of a given magnetic material with that of its susceptibility. Remember, the susceptibility with the increase in susceptibility, this is a very important equation. Let me give that to you in another ink for just highlighting it. This is an important relation which we'll be using to distinguish between the magnetic materials, which obviously is in the upcoming video in the next in the series. But till then, thank you for watching.